leaking trap valve is a common problem that can cause an inverted bucket trap to fail. The leak is often the result of damage or wear on the valve or the valve seat. If the valve doesn't seat properly, it will leak, and the trap may fail open, that is, with the trap valve in the open position. The trap will also fail open if the bucket becomes disconnected from the rod that connects it to the trap valve. Also, freezing and the damage it causes can be a problem with an inverted bucket trap, because normally the trap always contains some condensate. To prevent freezing, inverted bucket traps that will be shut down for a significant length of time should be drained. This is a float and thermostatic, or F&T trap. It's generally classified as a mechanical trap because one of its major internal parts is a ball-type float mechanism for removing condensate. However, it also has a thermostatic bellows that reacts to changes in temperature and is used to remove air and non-condensable gases. So in this respect, the trap is thermostatic. More information about thermostatic traps is given in the part of this topic that's entitled Thermostatic Traps. For now, let's look at how a typical F&T trap works. As condensate enters the trap, the accumulating condensate lifts the ball-type float that's attached to the trap's main valve. This action opens the main valve and allows the condensate to flow through the trap outlet. When steam enters the trap and reaches the bellows expands and the vent valve closes. At the same time, with the main valve open, condensate continues to flow through the trap and be discharged. The changing level of the condensate causes the float to rise and fall, which in turn affects how wide the trap valve opens and how much condensate is discharged. The buildup of air and gases in the trap lowers the temperature and eventually causes the bellows to contract, which opens the vent valve. Then, the air and gases are discharged through the trap outlet. The reaction of the bellows to temperature changes enables air and non-condensable gases to leave the trap and keeps the trap from becoming airbound. Air binding, or becoming airbound, is the condition that results when air fills a trap, closing the trap valve and keeping the trap from operating. If operating conditions cause condensate to build up to the point that the trap becomes waterlogged, the relatively cool condensate causes the bellows to contract, which opens the vent valve. Then the condensate drains through the open vent to the trap's discharge line. Dirt accumulated below the trap valve can cause an F&T trap to fail because large dirt particles can restrict the movement of the float mechanism. Failures caused by accumulated dirt particles can usually be avoided by installing a strainer at the trap inlet. Also, F&T traps can fail if water hammer or high pressures cause the trap's float to collapse. Other common problems that may be associated with F&T traps include disconnection of the float from the trap valve and damage from freezing if condensate isn't drained from the shutdown trap. In this part, we'll look at the operation of thermostatic steam traps. A thermostatic trap operates in response to the differences in temperature between steam, condensate, and air. One of the most common types of thermostatic traps is a bellows trap, which gets its name from the thermostatic bellows that is the trap's main internal component. At startup, the bellows is fully contracted and the trap valve is wide open. Condensate and air are pushed ahead of the steam directly through the trap outlet. Once steam enters, the temperature in the trap increases and the bellows quickly expands. As the bellows expands, the trap valve closes and steam is prevented from escaping. But as more condensate enters the trap and contacts the bellows, the relatively cool condensate causes the bellows to contract. As the bellows contracts, the valve opens and condensate leaves through the trap's outlet. Air and other non-condensable gases are usually cooler than steam, So they also cause the bellows to contract, which opens the valve and allows the gases to escape along with the condensate. A disadvantage of a bellows trap is that it generally can't be used in situations where pressures are very high because the bellows might collapse. Another disadvantage is that water hammer can rupture the bellows and cause the trap to fail. At any given temperature, the two different metals in the element expand and contract at different rates from each other. This causes the element to bend back and forth as temperature changes occur. Cool condensate, or air, bends the bimetal element one way to open the valve, and steam bends the element the other way to close the valve. Since the valve of a bimetallic trap is fully open when the trap is cold, this type of trap is effective during equipment startup because the trap can quickly eliminate air and cold condensate. But the trap response is more sluggish when steam has reached normal operating temperatures because time is required for the dissipation and absorption of heat that opens and closes the trap valve. Most thermostatic traps discharge condensate intermittently. The time it takes for condensate to discharge depends on the amount of condensate in the trap's drip line. The more condensate there is, the less time it takes to cause the trap to discharge. Thermostatic traps are also excellent at removing air. In this part, we'll look at thermodynamic steam traps. A thermodynamic trap contains a component such as a disc or a piston that responds to variations in velocity and pressure that are related to changes in state of the incoming fluid. We'll look at a typical disc-type thermodynamic trap. This example is a tilting disc trap. It's designed to handle low to medium condensate flow. As its name suggests, the trap contains a disc that lifts or tilts. The disc is the trap's only moving part. At startup, the disc rests on seating surfaces that contact the trap's inlet and outlet. With the disc in this position, the trap is closed. When relatively cool condensate enters the trap, the flow lifts the disc up and opens the trap. The condensate then flows through the outlet and is discharged. During normal operation, hot condensate entering the trap experiences an increase in velocity and a reduction in pressure. As a result, some of the liquid condensate changes state, flashing to steam. Because steam has a greater volume than an equivalent weight of condensate, the velocity of the flow through the trap greatly increases after the flash steam has been generated. This further increase in velocity reduces pressure on the underside of the disc. At the same time, flashing condensate flows out and causes a pressure buildup in the area above the disc. When sufficient pressure builds up here, while pressure on the underside of the disc has been reduced, the disc is forced down onto the seating surfaces, which closes the trap. The disc is held closed by the pressure of the steam that's in the chamber above the disc. When this steam condenses, changing to a liquid state, and the pressure above the disc becomes low enough, the disc rises and condensate flows out, until velocity and pressure conditions within the trap again cause the disc to snap down on the seating surfaces, closing the trap. If the temperature and pressure at the trap inlet remain constant, a disc trap opens and closes at regular intervals. That is, the trap operates on a time cycle. Because it operates on a time cycle, as long as the temperature and pressure at the trap inlet remain constant, a disc trap stays closed for the same amount of time, typically 5 to 10 seconds, each time that it closes. Condensate that comes to the trap in the middle of a time cycle won't be discharged until the pressure above the disc falls low enough to allow the disc to rise and reopen the trap. Since the movement of the disc cycles between the open and the shut positions, the discharge from the trap is intermittent. Many of the maintenance problems associated with thermodynamic steam traps are due to wear of the trap components. Thermodynamic traps are very sensitive to scale or dirt that gets lodged on the seating surfaces. For this reason, a strainer should always be installed at the trap inlet. The strainer should be cleaned or blown down frequently to be sure that it remains free of debris and does not become clogged. Thermodynamic traps that are exposed to adverse weather conditions, such as rain, may begin to cycle more frequently than normal. When this happens, the moving parts of the trap wear out faster simply because they operate more frequently. Manufacturers provide various solutions to this problem. Some manufacturers make thermodynamic traps with double-walled bodies. Steam or condensate that enters a double-walled trap first flows around the outside of the internal parts and then into the trap. The warm condensate or steam keeps the internal parts at a relatively even temperature. Another way to protect a trap from adverse weather conditions is to use a bonnet cover. The bonnet is the top of the trap casing, and a bonnet cover is a metal cap that's placed over the top of the trap. The airspace between the cap and the trap body acts as an insulator and protects the trap from the weather.